Everybody, and welcome to our video for lesson 3.2, which is solving linear systems algebraically. So you're going to use line paper for your notes today. This is going to be a review from Algebra 1. We're going to work on substitution and elimination with two equations and two variables. And this is really setting us up for larger algebraic systems, which we're going to solve in future lessons. So take a moment to set up your note sheet with the date and the lesson on the top, and the first line should be the I can statement. You can pause your video to set that up and then resume. So the first thing we're going to look at here is deciding whether to use substitution or elimination for a system of equations. And the way I make this decision is if I see a variable that's alone, in other words, that has no coefficient, you're probably better off using substitution. However, in a case like this one, where all the variables have coefficients, we're going to choose elimination as our method. So I'm going to rewrite our system on this side, negative 2x plus 4y equals 15, and 6x plus 12y equals 45. And what I notice here is I can't immediately add or subtract because none of the variables will cancel themselves out. So the first thing I need to do is multiply so that I can get rid of one of the variables. I'm going to try to get rid of x in this case, so I'm going to multiply by 3 so that my equation becomes negative 6x plus 12y equals 45. Now, if I add these two equations together, we can end up with the x's eliminating, and we've got 24y equals 90. When we divide both sides by 24, we get y equals 90 24ths. And you can pretty easily simplify that by dividing everything through by 6. And you'll end up with y equals 15 fourths. So that's one variable. And then remember, we need to find both variables. So we're going to plug 15 fourths back into either equation for y. I'm going to choose to use the top one. So I've got negative 2x plus 4 times 15 fourths equals 15. And the nice thing here is 4 times 15 fourths is just 15. So I've got negative 2x plus 15 equals 15. Which means that negative 2x equals 0, and x also equals 0 for this problem. So our solution to this problem is y equals 15 fourths and x equals 0, which you can write as a single point, 0, comma, 15 fourths, which means in this case, our lines will actually intersect on the y-axis. So another example that we could look at here is 3x plus 6 equals 7y, and x plus 2y equals 11. Now, you could certainly use elimination or substitution for this problem, just like any system. Our goal is to choose the most efficient one. For me, noticing right off the bat that x is alone tells me that I might use substitution for this problem. And specifically, I'm going to solve the bottom equation for x. X equals 11 minus 2y. And once we do that, we can then just take that 11 minus 2y and plug it into the top equation for x. So we have 3 times 11 minus 2y plus 6 equals 7y. Now we just need to simplify and solve this problem. So we have 33 minus 6y plus 6 equals 7y, which also tells us that 39 equals 13y. And when we do the division, we end up with y equals 3. And once we have one variable, remember that we have to get both. So I'm going to take the y equals 3, and I'm actually going to plug it right back into the equation that we already solved for x. So, and the reason for that is just because it's so much more efficient. So x equals 11 minus 2 times 3. In other words, x equals 5. And that gives us the solution to our problem, which you can write just like this, or you can represent it as the point of intersection, which would be 5, comma 3. And that's just to help you remember that it is, in fact, a point of intersection. So the next thing I want to look at is why solving algebraically actually works. And we can think about this from a graphical perspective. And I'd like you to think about it for a second. So the question is, what do you think the graph would look like if we added these equations? And what do you think the graph would look like if we subtracted these equations? So I've got these two equations on Desmos, and I want you to think about what the result would be if we add the two functions together and what it would be if we subtract them. So it might be a good idea to pause the video and think about that for a moment. All right, so I'm going to start by adding the two equations together. And if I add the two equations together, I end up with 2y on the left side equals, and the x terms cancel out, so we end up with 2y equals 2. And if you notice, that results in a horizontal line that goes through the point of intersection. And similarly, if we had used elimination to subtract these two functions, the y terms would eliminate themselves. So we'd end up with 0 equals 8x minus 8. And if you think about that, that's eliminating the y terms, which results in a vertical line that also goes through our point of intersection. So the reason elimination actually works is because you're essentially eliminating a variable to create a horizontal or vertical line that goes through the solution point to the system, which I think is actually pretty darn cool. So the last problem I would like you to try is I have two examples here. And I would like you to decide for each one whether you're going to use elimination or substitution. And then I want you to solve both examples right now before you resume the video. And then I will walk you through each example and see if you end up with the same solution that I did. So pause the video and give them a shot. All right, so I'm going to write up the solutions first, because if you got the same solutions as me, you can end the video here and don't need to watch me work them out. So the solution to the first problem is -1, -1. And the solution to the second problem, you should have found that all the variables disappeared and you ended up with no solutions. So if you got both of these right, you can stop the video and move on to your homework. Otherwise, I'm going to show how I would solve both of these problems now. So for the first example, I noticed that none of the variables are alone, which tells me I'm going to use elimination. And in this case, I need to multiply both equations to end up with a place where I can eliminate the variables. And I'm going to try to eliminate y by multiplying through on the top by 5 and on the bottom by 4. And that leaves me on the top with 35x minus 20y equals 15. Now -15. You may have done this a little bit differently than me, and that's okay. There's definitely multiple ways to do a problem like this. On the bottom, I've got 8x plus 20y equals -28. And because the plus and minus don't match, that tells me that I'm going to add to eliminate. So in this case, I'm going to end up with 43x equals -43. So when I divide through, x equals -1. And I'm going to plug x equals -1 back into the original equation. So, and I'll just use the top one, 7 times -1 minus 4y equals -3. So -7 minus 4y equals -3. I'm going to add 7 to both sides. -4y equals 4. And that tells us that y equals -1, which leads us to our answer of -1, -1. Now for the second problem, I'm going to notice that x is alone, which tells me I'm going to use substitution for this problem. Because I've got x equals 12 plus 3y, which I'm going to plug into x in the second equation. So we've got -5 times 12 plus 3y plus 15y equals -45. And when we do our distribution, we end up with negative 60 minus 15y plus 15y equals negative 45. And you'll notice here that the 15y and negative 15y cancel out, and you're left with negative 60 equals negative 45. But because those two things are absolutely not equal, that tells us that our answer to this problem is no solutions. Which means graphically, those two lines are parallel and would never intersect with each other. So that's the end of our video for 3.2 on solving systems algebraically. So go ahead and get started on your homework, and as always, let me know if you have any questions.